Hello and welcome everyone to Flowserve's Destination Innovation Virtual Experience. I will be your host, Hugo Castrejon, a Senior Training Specialist within Flowserve's Aftermarket Services and Solutions Group. I began my Flowserve career within groundwater development and water resources, primarily focusing on vertical turbine pump and submersible applications before joining the power generation group. There, I expanded my focus to include large multi-stage between bearing pumps. And now I look to impart that pump knowledge and industry experience to trainees. I have enjoyed being a trainer over the past couple years, and I am honored to be hosting this virtual training today. I will be introducing a decarbonization case study on using speed control for energy savings. This case study will span a brief introduction into optimizing a pump system, and more specifically, into the savings that can be achieved through such an optimization process. So we will touch on the feasibility of candidacy selection, the cost of running inefficiently, and where savings can be attained. So let's begin. In order to determine if a pump system is a proper candidate for optimization consideration, it is best to litmus it as feasibly suitable. For example, does the pump exhibit excessive wear and tear from cavitation, or is it sufficiently throttled away from its best efficiency point? If so, the pump may be a viable candidate for optimization. I say maybe because mission-critical pumps, or those having restricted site accessibility, are only suitable for optimization during the next pre-planned turnaround or shutdown, which is a great opportunity. This allows for the time to thoroughly and strategically weigh the legitimacy of the optimization in question. Often the largest recurring cost to operate a pump system is related to the energy consumed by the driver. For the basis of simplicity, this case study will focus on an electric motor driving a pump. An overall rate of 9 cents per kilowatt hour will be assumed, though this will vary greatly depending on what is negotiated between the site and the utility provider. Things that may impact the overall cost of electricity will be the usage history, the rate schedule negotiated, the time of draw throughout the day, and potentially the percentage of green content supplied on site. There are two basic methods for estimating pump power consumption and one choice for empirically determining its consumption. The first two can be conservatively determined from either the motor nameplate information or the pump performance curve. The latter requires on-site testing for current and voltage draw to the driver. To get accurate data from the test, it is best to allow for a sufficient time span of data to be recorded to better understand peak loads and seasonal demands. For simplicity's sake, the motor nameplate information will be used for the case study to follow. This is a graphical representation of how energy is wasted across a valve when throttling away from the design duty point. The yellow area highlighted represents the destructive energy wasted from throttling in the form of noise, vibration, and heat. Although the valve takes a beating, the accompanying pump and its seal will also have to endure exposure to such operating conditions. So what can be done to limit the destructive force upon the valve, pump, and seal? Depending on the situation, suitable options may include a proper hydraulic re-rate of the pump, a redesign of the pumping system, or implementation of speed control. Bearing this in mind, the case study opens with a bad actor pump at a pulp mill. The pump specifics are given, and what stands out is that typical operation is in the range of half of the design flow. Since operation is sufficiently far away from design, cavitation-induced downtime is frequent. The customer is expecting a budget-conscious solution to extend mean time between failure that effectively justifies the capital expense for the optimization itself. In order to cut the power demand and increase uptime, the solution is to install a variable frequency drive, or VFD for short, paired with a smaller motor. This allows operations to slow the pump to the desired flow and not throttle the excess head, highlighted in yellow, promoting the life of the pump, its seal, and the valving in the system. Using the nameplate data to estimate our energy demand, the horsepower must first be converted into kilowatts of electricity. Then the efficiency of the drive at the load rating must be applied. Thereafter, the cost of electricity can be determined from the overall price per kilowatt hour of usage, given in this example as $103,885 annually, though bear in mind that those using the metric system can simply avoid the first conversion from horsepower to kilowatts. Now repeat the calculations and compare this to the potential energy savings for using speed control. The total estimated annual cost of electricity is now only $92,865. We see that there is over $11,000 that can be saved annually in energy, though that is only part of the savings picture. So let's take a deeper dive. Taking a closer look, there is greater savings stemming from the speed control in reducing maintenance expenses and typical downtime annually. In fact, the capital cost of implementing the solution, that is, the $88,000 for purchasing the equipment and another $45,000 for installation, results in a net savings of $463,000 that is achieved in the first year of installation. Thereafter, the repeated savings of $11,000 of electricity and $135,000 of maintenance will be achievable. This means that without the savings of production uptime, the solution will pay for itself within the first year, making it an incentivizing option for savings and reduced carbon footprint. As a training specialist, I can assure you that there are a host of curriculums offered by Flowserve to provide you with the fundamentals to exact such results on site. These courses can be found online at academy.flowserve.com, or you may reach out to your local Flowserve salesman for any enrollment questions necessary. For any questions into site-specific situations, please email me at the Flowserve email provided. Thank you, and I hope you enjoyed this presentation.